Thank you very much for your invitation. I really enjoyed this workshop so far, and I'm going to offer a different perspective. I'm not going to talk about learning, and I'm not going to talk about simulation. I think we heard a lot about this, and there is amazing work that is being done. I'm going to talk about motion planning and offer a perspective that I think bears some relevance to what the community is trying to do today with benchmarks and learning. So motion planning is a subfield in robotics. We are dealing with a very, very specific problem. This is where we started. Really, robots that it was called the piano mover problems. Remember, it was moving a piano in an environment, and you just had to make sure that this piano did not have any collisions with the environment. And then we inserted kinodynamic constraints, and we wanted to make sure that we have a plan for going from A to B without collisions, respecting all the constraints of the system. So there is a big area, and many people have worked on this, on the topic of motion planning for many years. Today, we see mainly focus on systems with high numbers of degrees of freedom, like the ones that you are showing, that I'm showing here. Look at this robot in the middle. It really goes through a narrow passage in the space, and it is a difficult motion planning problem to execute, even when you have a model of the robot and the environment. The last example on the right shows Robonaut2, a robot that is that was built by NASA to work on the space station, a 15 degree of freedom system, moving, however, in a very confined and known environment. Still, planning for such a robot is a challenge. So in motion planning, traditionally, interesting problems include high dimensional problems. So robots with 7 degrees of freedom or more, I mean, motion planners researchers in motion planning will consider planning for a 2D, 3D robot solved. But 100 degrees of freedom is kind of interesting. And this may not be just a robot, it could be a protein. I mean, people like me have had a second career actually taking some of the techniques in motion planning and applying them to understand motion and shape of molecules. We also are interested in having constraints in the environment, so obstacles, manifold constraints. You can hear I'm showing an animation with manifold constraints, so geometric constraints. This is a problem that has 140 degrees of freedom. So all these links hold the plate, and they really need to hold it and maintain this constraint, otherwise the system will not work. Kinodynamic constraints were shown in the previous example. And the community cared about pathological environments, backtraps, narrow passages. I mean, how do you plan for these cases? How do you design algorithms that are general and plan for these cases? Classical assumptions include good models, good controllers. Often a quasi-static assumption was done, full observability, and simulators are used, and they are used for propagating the system, for propagating hard to model systems, systems for which we do not have equations, like, the car that you see here was not going fast enough, couldn't get off on the ramp. And now a simulator is used to understand how it gets off the ramp, but really, the visual element was never considered. I mean, it was never the goal for things to look nice, just to make sure that the physics were taken into account as best as possible. So for a very large of a set of planners, which are called sampling-based motion planners, and with which I have been involved from their inception, we start with an abstract configuration space with one dimension for each degree of freedom of the robot. The configuration space obstacles are implicitly defined, by configurations in collision. So you have a collision checker that tells you if you're in collision with an obstacle in the environment or not. The problem is defined by the workspace, the start, and a goal, and we are looking for a collision-free path. The general way that the sampling-based motion planners work is as follows. You sample a configuration, and somehow, and I will not go into details, you try to extend or connect new configurations, extend this configuration to new parts of the space, connect to an existing graph or a tree. And this is a very extensive and very general framework for search, as you can understand. And there have been successes. And actually, there is not one sampling-based motion planner. There are here, I stopped counting at some point. I mean, there are hundreds, I would say, at this point. And because the way that these samples are generated, we face the problem, or how do you compare across all these different planners? So how do you compare? So let's talk about benchmarking for this particular problem. Of course, there are caveats I recognize, but I want to focus us on one thing. I want to make a point. I recognize that motion planning is just one part of the puzzle. Yes, we are talking about systems, and the assumptions that these algorithms have don't always hold in the real world. But let's look at this motion planning problem. The planning community broadly cares about generality and efficiency. How many different problems, different robots, and how quickly can this be solved? So opening a drawer, that means opening any drawer with any robot. We want an algorithm that will do that, given, of course, a model for the drawer, how it can move, and a model for the robot. Many methods, so we care about if the problems can be solved, if the algorithm generalizes without much intervention, and solves for a different robot and in different environments. And many methods also care about cost and convergence over time. What did the benchmarks include? Well, tasks, but the tasks here in this area are defined with start and goal regions. Okay, this is different from how tasks are unified and brought in learning, and fully modeled environments with interesting features like narrow passages. And when we talk about benchmarking, we talk about use of statistical methods. So we report medians, confidence intervals, success rates, and all that. And you can see a picture here. On the x-axis are different kind of planners. On the y-axis is time. How do they perform on a particular problem? You can get an idea of which planner to use for this specific problem. The OpenMotion library that was just mentioned was and is still an effort to systematize and compare sampling-based motion planners. It grew out of frustration because at some point there were papers that were appearing at robotics conferences, and every paper claimed that it was better than the paper before it, but it was not clear why this conclusion was made. The library was it's about 10 years old right now, but still actively maintained and used. And as I said, it provides implementations of state-of-the-art sampling-based motion planners. So by forcing a common interface, by forcing all these planners to use the same core concepts for collision checking, we can arrive to a comparison of these planners. And this is not done in OMPL, but it's done in a companion software suite, which is called Planner Arena. So in Planner Arena, you can take the planners that OMPL has. You can input your space, your problem, and it will give you back examples like this one, where you can get box plots for the performance of the planners. And there are, as I told you, several different planners, and OMPL currently has more than 60 of these planners. And if you are talking about an asymptotically optimal planner, it will give you the best cost as a function of time, because it's not only important to choose a planner that is asymptotically optimal, you probably want to choose one that has good convergence properties for your particular problem. So this infrastructure, let's say, has been used a lot, but still, I must say that there has been significant resentment from the community. Sometimes we had requests. This is an open software, an open source library. We welcomed from the beginning contributions. People would send us their code. They would need to use the basic primitives for the library so that we can compare algorithms. And we did a code review and then incorporated the planner in the library. Many people withdrew their planners because after the planner is incorporated to the library, then you go through the benchmarking and the results were not always what they wanted to see. It has been very interesting to see that, and it happened multiple times. So the benchmarking that is done in motion planning is very different than the benchmarking that is discussed here. Many of the problems that we look at are not realistic, okay, puzzle boxes. They're hard and interesting, but they're artificial. So the assumptions are very often implicit, and it is actually implicit in learning too. For example, if you are talking about manipulation on a table, okay, tabletop manipulation, this is a very different kind of problem than going, in a building and finding into a particular room and opening a drawer. These are very, very different problems. But sometimes, and tabletop manipulation sometimes can be very easy compared to opening a drawer or picking something from a shelf. And they are not always discussed, these assumptions. The other thing is that expert knowledge is needed to understand and tune the planners. And unfortunately, many, it is hard to do, and many unavoidably use a library without this, the tuning of the planners. And different environments are needed, and variations in each of these environment is very, very important. It is a lot of care needs to be put on making conclusions about different methods. Here I have an example which is a real example you can find in our papers. This is a planner that has been run of five different variations of a problem. And if you look at this, you will go, oh, of course, I'll use the green planner, right? But if I show you the whole picture, if you do this analysis on variations of the problem, you see that at the end, the conclusion is no, the yellow planner is what I should be using and not the green planner. But it's hard to get to this kind of analysis, even for a very specific problem. I talked to you about a motion planning problem that has a lot of constraints. We have, as a group, done a number of things to address some of the difficulties. I'll discuss two of them: the expert knowledge that is needed to understand and tune the planners. Okay, this is something we've run to many, many times. OMPL, for example, has some default parameters that honestly students in the lab found they worked and they set these planners. But if you are going to use this planner, you should not be relying on these standard parameters. You don't need to do that by hand. I mean, now we have a software which is called Hyperplan, and really it uses techniques for learning. This is a hyperparameter optimization that you're doing, and you're applying them to planning. So the Hyperplan using a Bayesian optimization and hyperband, and it can produce order of magnitude speed up over the default parameters of OMPL. So if you are using one of the motion planning algorithms, at least make a minimal effort to tune the planner. And typically we use all these planners with octomaps now, not geometric models, but octomap models from of the environments. And I'm not showing you the details. You can find them in the paper, which was at IRIS last year, but it's a huge improvement. Okay, the baseline, which is the standard parameters of the planners, look at the amount of time you're taking, and this is what you get after using Hyperplan. So at least do a best effort to use the planner correctly, so that the comparisons that you're going to make between different planners, among different planners, are trustworthy. And it can be done automatically. I mean, you don't really need to hand tune the planners. The second thing, the different environments that are needed and the variation in each environment are very important for understanding what kind of planner you're going to use. And remember, I'm still talking about a much simpler problem than what has been discussed here in this workshop. So in order to run motion planning with different environments and have the ability to work with Move It and to execute it to a real robot, you need a lot of, let's say, machinery. And one of the machinery that we are offering right now is Robowflex, which is really a wrapper. It's Move It made easy. I mean, this is the shorthand for Robowflex. It makes it easy to copy, modify, collect environments from simulation or real data. So that when you are going to evaluate a motion planner, you are going to evaluate it on different environments and slight variations of these environments. And this is, I think, why this is one of the things that the organizers of this workshop asked me to talk about, the MotionBenchMaker, which is a suite which is a tool to generate and benchmark motion planning data sets. This robot benchmarker takes in as input a robot description and a scene description. And what it does is that it samples the scene and creates a set of scenes that are around the original scene. It consists, so it's a systematized, a procedural way of generating benchmarks. It has a problem generator that is agnostic to the robot that you're going to use. And it has also an octomap generator so that in the end you can use an octomap of the scene and plan using the octomap. This work was published at Robotics Automation Letters and was also presented at ICRA this year. Generating problems with variation, as I showed you before, is very important for us, and the plans do change a lot, even with small variations. So you need to understand what is the average performance of your planner. The figure of the right, the robot was getting to the obstacle from the left. Here it's getting from the right side. I mean, this is yet another way of reaching the end effector to a particular pose. And this all can be generated, these problem variations can be generated automatically by OMPL. So Robot benchmaker, so that you can have the same problem, let's say, but you can have different robots that deal with the same, this problem. And usually manipulation is something that presents more difficult examples, more difficult benchmarks for motion planners. So these are some of the kind of benchmarks that we generate from the same nominal scene, changing the scene. We sample the positions of the objects in the scene, but also URDF constraints, so that we can have kinematic constraints like opening drawers and boxes and things like that. So here is a predefined set of interesting problems for robot motion planning. I'm not claiming that this is the answer to benchmarking for motion planning, but I want to tell you that it took about 20 years to get here, because there was not agreement in the community about what to benchmark and how to do it. And it took also collaboration between 3 different groups: my group, Mark Toussaint's group, and Mike Glacier's group at Wisconsin, to get to this. So if you're getting into this endeavor, it is a lot of work and a lot of thought that needs to be put on how to do things. And now modern motion planning techniques really, are not covered by what I just said. I mean, now we want to plan under uncertainty in dynamic environments. We want replanning. We want planning for long horizon tasks. They don't share the assumptions that I talked about that created, let's say, a motion benchmaker. So geometric constraints, I want to talk a little bit about manipulation planning, and I will finish with that. So manipulation planning for somebody like me means that you get the state of the environment from, let's say, state A to state B, which may mean a number of short motion plans that need to be stitched together in order for something to work. And you saw here one example, which we called multimodal planning. So you have to understand where to grasp and how to grasp, and how to move the object from an initial to a goal configuration. And here you can see a more complex task, which is you need to specify what the task is somehow, which is to to move the stack these two objects. But first you have to clean the table. So you have to find a way to specify the task. You have to find a way to understand what operations you need to do and how to sequence them. And there are two things here. There is the discrete part and there is the continuous part, the motion planning part. The discrete part can be fairly complex, and sometimes let me start from the geometry, which is easier to explain. The geometry, you may want to do something, but you cannot do it. Okay, it may not be feasible. It will have helped your task, but it's not feasible. So you have to think about what to do with the discrete part of the task so that each of the steps that you need to execute actually can be executed by a robot. So it is something that we've been working on for several years. We call it task and motion planning. Some of us call it task and motion planning. Some call it multimodal planning. And there are methods that solve, and these are methods that solve these bigger, more realistic problems that we want to get at. There is additional complexity in connecting abstractions, the actions and the tasks to the geometry, grasp placements and motions. And I didn't hear anything about these topics during this workshop. So there is a long way to go, I think, for understanding how to represent all these things. And this is part of the difficulty. And maybe as it was discussed during the debate, it will lead us to more interesting problems, to understanding what are the problems that we are interested in solving before we get to create benchmarks and solve them. Our experience has been that for task and motion planning, which is a topic I've been working on for the last, I would say, 5 to 6 years, almost every method that exists in the motion planning community picks slightly different set of assumptions. So they relax something, every group relaxes a different thing. So we have different samplers, the definitions are a little bit different, the models are a little bit different, discretization is done a little bit differently, and it's impossible to compare. In 2017, we had been having a series of workshops at RSS, the Robots Science and Systems Conference, on task and motion planning. And in 2017, we decided, okay, let's talk about benchmarks. And we brought the community together and we said, all right, we need some task and motion planning benchmarks. And there is a paper and there is still a website that came out of this work. In my opinion, this effort failed. It's unclear what benchmarking means for manipulation planning, and it failed for many reasons. Some were technical. There is not a uniform format for specifying this problem. Some were actually the fact that it's such a broad area. When we started understanding all the different assumptions that the different groups were making when they contributed the benchmarks, and other groups started pointing them out, these benchmarks were never updated. Okay? The groups did not have the will to update the benchmarks because this, did not really help their work. And it's also a lack of scope. What is the scope that you want to these problems to capture, the task and motion planning to capture? Again, not clear, and I think it is interesting to think about this problem. In October, we had a kind of a similar workshop at IROS, talking about evaluating planning performance. And what we wanted to discuss, and we discussed what are appropriate comparisons between learning methods and algorithmic methods, which is what I'm discussing here. And there is really not an agreement on what are the baselines, what are the configurations, what are the data sets. Are the problems and the tasks the same? Sometimes we see a learning method being compared with an algorithmic method, but is the problem the same? Are they comparing for the same problem? What metrics to report is also very interesting. What is success? I'm still not clear what is success. They also, something else that came out of this workshop, which is relevant as we move to robots and learning in the real world, is that diverse motion planning applications require diverse metrics. So it's a different thing to do manipulation on the table. It's the different benchmark is needed for social navigation, where social norms need to be respected. A different thing, a different set is needed for multi-robot coordination, for example. For surgical robotics, safety is an issue. It's a totally different set of things that are needed. And I'm afraid that I have to say that these fields don't agree on specific benchmarks, but I think that what we can do as a community is that agree on the motivation and the interpretation of benchmarking. And moving forward, I think there is a lot of room for meaningful and insightful comparisons across motion planning, task and motion planning, and learning. These fields have different priorities, but can learn from each other. We need to understand what is the shared space of evaluation methods, and also a better communication of the assumptions and the properties made in each of these field. Shared and interoperable tools for benchmarking, datasets, and evaluation methods will, of course, help. So I told you what is the motion planning benchmaker, and that there was an effort by 3 groups and we got to something. But honestly, I have no idea how to get to a manipulation planning benchmaker. Okay, how to create manipulation planning benchmarks. What robotics tasks are interesting in general, what robotics tasks are interesting to both learning and planning communities. I feel there is an intersection, but I don't think we've pinned it down. And what are specification, of course, shared specification formats that will help us get to an understanding of where we are as a field, and also how to combine the learning and the planning communities. And I will stop here, and thank you all for your attention just before lunch. Thank you for staying. Thanks. I'm happy to take questions. Okay.
I think one thing that was really interesting you mentioned was about tuning the parameters for motion planners for a lot of these benchmarks. Do you see that's something that should always be done? And if so, how do you, is there a sense of I want to tune on some subset of paths and evaluate other paths, or do you always should tune parameters for the benchmark path?
Well, first of all, for sampling-based motion planners, you should always tune the parameters. I mean, you just cannot use these planners out of the box without any help. And you should tune the parameters for the set of problems that you're interested in doing. You don't have to do this manually. As I told you, there are a set of tools for doing it, but I think this is something that has to be done. Now, with the learning, for example, if the learning is looking at a certain set of problems, these problems can be used to also tune motion planners, and then you could have some kind of an understanding on what each of these fields can do. Yes.
I love the last question. You don't know how to start a manipulation benchmark. You have a tremendous history on trying to figure out how to work together on these problems in the past from motion planning. Have an intuition about how to get started.
Well, I would like to get started. I don't have, I think there needs to be an understanding of what are the priorities of the different fields that are contributing to manipulation planning at this point, because each of these fields has different priorities, and that's actually good. Okay, that's not a minus, that's a huge plus. But there needs to be an understanding what are these different priorities, and I think we need to modulate to create modules. I think this is a problem for which we cannot go for one approach for everything, but we need to exploit modularity. And there is a lot of modularity in this problem. And certain techniques are better for certain modules than others. So establishing a common language and understanding what are the different priorities, because now everybody is trying to do everything. And I don't know how far we can go with that. Is important.
So when we try to understand, we have kind of engineering modularities that we have.
Yes.
in applications that don't correspond to the actual task we're trying to solve. And if we can look at the ways that we're working in common modularities, we can find ways to work together.
Yes. Mhm. It's one way to go.
Can I ask one question? Early in the talk, you were talking about how motion planning was, especially sampling-based motion planning, was never designed to look good. Like it was designed to satisfy these geometric constraints, but not necessarily like the motion. But I guess what I'm wondering is, as robots enter the real world and like are interacting, we want to have them interact with people, especially like manipulation settings, things like that. Do you think there is a space for sampling-based planners to like look good? I guess by look good, I mean like be legible.
Yes. So I think yes. And actually the original planners, for the original planners, there was no notion of it has to be a nice motion. At that point, there was no solution. So we went from not being able to solve the problems to having a solution. But nobody said that you should be using these planners that were developed 20 years ago for the problems that we need today, where we care about the quality of the path. There are sampling-based planners, asymptotically planners, and optimization-based planners that can be used. They are just far more complex. All right, you pay something, okay, and the original plans were really simple. They did the job. They did a poor job, okay, but they solved the problem. If you want to use motion planning in today's context, you need to go to these more complex planners. But for these more complex planners that are in OMPL, and we can talk about it, you need to tune them. So you need to understand what is it that these planners are doing and why are they doing it and how do you tune them? If you don't do it and you don't spend the time, well, that makes no sense. You see, so there are many different planners. There are some that are very fast, very simple. They help the community really move forward. But this doesn't mean that today we should be using the initial versions of these planners. They're far more interesting planners, but you have to pay somewhere, okay? You pay in the complexity of the planner and you need a more mature understanding of the problem, right? But these planners are available and the community is not using them. Why? Because you need this extra understanding. And that's why we are trying to give you through the Hyperplan and through the tools that we have developed, an understanding of what is it that you should be using. I am very frustrated sometimes when I see comparisons with planners that were developed 20 years ago, the moment that there's so much better methods that can be used today. And if there is at some point a connection of the learning community with the motion planning community, if planners are used to create benchmarks for learning, it would be really sad to see these original planners being used because they do not provide the quality of paths that we need today. The same for manipulation planning. If we are going to have a connection between learning and planning in that context, we have to go with the right planners.
So if someone today wanted to do that, like, okay, I want to go out, I want to make a benchmark set, and I want
For what?
for like, right? That's a good question. I guess that's the whole point of the problem.
Mhm.
But so I shouldn't just ignore that. But for some manipulation task, like task X, I don't know what the task is right now, but how should this person go about choosing which one of these planners? Like, do they go to the OMPL website? Is that the place to start?
That is one way to start, yes. And if you go there, you'll see the planners that are there, the evaluation tools. You see pointers to other software that is offering different options. But yes, work needs to be put in choosing a planner. You cannot just choose a random, an easy planner, maybe the ones that they're used a lot because they're very simple. They're simple to implement. I mean, there's a real power in it. Okay, this is really very, very good. It helped the community tremendously. But now we have to go past these planners and use what is appropriate for the problem that we need, that we have to solve. Yes.
Given that we identified this mismatch in different academic communities,
Yes.
how they approach the problems, do you see an opportunity for the industry to perhaps drive some of these challenges? And,
Yes.
is it also dangerous, perhaps over focus on specific tasks?
On specific tasks, right? Focus on specific tasks. Yes, I think it is dangerous to focus on specific tasks, and if you're also a good person to answer this question, but if we focus, if we go too much down on one category of tasks, with learning, for example, we are, I think, going to lose this idea of generalizability that exists in the motion planning community. So a partial answer to the question. Grasp it. Mm-hmm.
There's these sort of assumptions which can apply to those solutions. And I want
Mm-hmm. Yes, absolutely. And you should be using the simpler solution. You should be using the simpler solution. That's why I'm saying, the comment I made it before is that, we cannot be stuck with planners that were developed 20 years ago because they were fast, because now there are simpler solutions. Sometimes it could be an optimization-based planner that is good, or a planner that, maintains contact. Okay, yes, these are the solutions that need to be used. Yes, I agree with you 100%. Yeah. Assumptions. Yes. Yes. Yes, yes, I see your point, and I hope this collaborates my discussion on how difficult, even for this problem, it has been to create benchmarks. And also that maybe we won't get to a benchmark, for everything, but what we could do is understand, have an understanding of what is it that we want to do with a measure, with a benchmark, and an understanding of the goal. What is the goal that we have with the benchmark, and some agreement on the methodology and the assumptions that are made.